7C, applications of differentiation. So we learned how to differentiate sine, cos, and tan last lesson. Today we've got tangents and normals up there. So remember, you'll have to find the derivative first, and then use that to find the equation using the y take y1 equals m bracket x take x1. So straight into examples. Number 1, find the equation of the tangent to the curve y equals 2 sine x at the point P where x is equal to pi over 6. So, because we're trying to find the equation of a tangent, I need a derivative. So we're looking on our study sheets, and I want to differentiate 2 sine x. What do I get? Well, the 2 is just sitting at the front. So how do I differentiate the sine x part? It becomes cos x, correct? Okay, now that is the gradient for anywhere, any x value. I want to find it specifically when the x is equal to pi over 6. Okay, so we're going to sub this in. Y dash equals 2 cos pi over 6. If your calculator's in radians, you can type that in. What do you get? Correct, root 3. Okay, now I'm after an equation, but to use this formula here for an equation, I need to have a gradient, got it? But I need a point. I don't have a point, I only have an x value. I need the y value to go with that point. So I'm going to sub that into my original equation, there it is, to find the y value. So I'm just going to write also y is equal to 2 sine pi over 6. Type that one in. It equals 1, correct. All right, so over to the other half of that space there. We are going to use our formula. You might want to recap here that the m is the root 3 and the point is pi over 6 comma 1. So in our formula, we will have y take 1 equals, gradient is root 3, x take pi over 6. I'm going to leave this in gradient intercept form. So let's expand it out and move the 1 over to the other side. So I'll do it in one step even. Y equals root 3x minus root 3 times the pi over 6, and then plus the 1 on the end. So this part here, there's my gradient x, so it's the mx. That whole thing there is the y-intercept. It's just not a very nice one. Question 2. Find the equations of the tangent and the normal to the curve y equals cos x at 2 points. Oh dear, do you know what that means? 4 equations that I'm being asked to find. Okay, because I want the tangent and normal here and the tangent and normal there. 4 equations. So the first thing I need is my derivative. So y equals cos x. What is the derivative of cos x? Who said, sorry, what now? Negative sign. Good. Okay, let's start with the point A. So minus pi on 2 comma 0. I'm going to do that one first and I'll come back for B. So if I sub in the x value, my gradient will be negative sine of minus pi over 2. Calculator time. Got it? You didn't think it was right? Oh, okay. It's 1. Okay, so let's do the equation of the tangent. Equation of tangent. Okay, so this is using that m is equal to 1. And the point A here. M is 1, point there. Into the y minus y1 formula. So it will be y minus 0 equals m is 1, bracket, x minus minus makes a plus, pi over 2. And y minus 0 is just y, and the 1 doesn't really do anything when you times it out. So there's the equation of my tangent. Let's do the normal. Equation of normal. Okay, what's the gradient of my normal? -1, excellent. And using the same point. So it will be y minus 0 equals -1, x plus pi on 2. So the only thing that's changed is the gradient. And again, that's just y on the left. And it'll be minus x minus pi on 2 when you expand the minus out. That was all right, wasn't it? Take 2, do it all again for the second point. Almost seems silly to do that again, doesn't it? But anyway, all right, let's go now when b is equal to pi over 2 comma 0. Maybe I should do it without talking. You guys should do it at the same time and see if you get the same things. Let's go. I'm going to freeze that. You can't copy. There you go. Now you can't copy. Anyone got the first one? Yes, good job, Grace. There's the first one. Then use your perpendicular gradient, which would be a positive one, to do the normal. Done? All right, there it is. Okay, moving on to part B. There's a part B. Show that the 4 lines form a square and find the other 2 vertices. Okay. All right. Oh, I wish this wasn't on 2 different pages. That's annoying, isn't it? Okay. All right. The first equation that we were given, or found, sorry. Look back. Was y equals x plus pi on 2. Okay. So that is a line that has a gradient of 1 and a y-intercept of pi over 2. So pi over 2 is going to be here. There's my y-intercept. A gradient of 1, I could come over, what would that, because that's going to be going that way, what would that value be there on my x-axis? Yes, good, -pi on 2. And that would be my first equation of my tangent that I found. Okay. Then the second one was y equals minus x minus pi over 2. So that's a -1 gradient. Minus pi over 2 is down here for my y-intercept. A -1 gradient. -1. So it's got to slope back that way. And what's it going to go through? That again, because that's going to have the same rise, the same run, but in a negative slope. Okay? So it's going to go like that. Okay, now this point over, I'm going to change colours. This point here, which was minus pi over 2, 0, that was the point A. So this was A minus pi over 2, comma 0. So that was the first point that we were given. And this was my tangent, and this is my normal. So I do know that these things here are making a right angle. Okay, so now we move over to point B, and point B was the point pi over 2, 0. So it's going to be over here, pi over 2, or if I write it, b is pi over 2 comma 0. Okay? My equation of my tangent was negative x, so negative 1 gradient, plus pi on 2. So the positive pi on 2 up here is my intercept again, and I want a negative 1 gradient, which means going through there. Okay? So this is the tangent, and the normal was x minus pi on 2, so it's down here, minus pi on 2 is the y-intercept, positive 1 gradient, so here we go, we're closing in the square. Okay, and they were a tangent and a normal, so we know that that's a right angle. Okay, so pretty, hopefully it's pretty easy to see that it's a square, because from the center it's pi on 2 distance the whole way around, so all the sides would be the same length, and because of these right angles, we do know that it will be a square. Just to help another little picture of what we've done here, the starting curve was cos x. Cos x looks like it goes through 1, which I'm going to put there, and it goes like that. So if the pink curve is a very bad cos x, these ones are my tangents, and those ones are my normals to the curve at those points. Yeah, and it makes a square. I was asked to find the other two vertices. So I've got A and B, so I'm going to write the coordinates of those two there. So other vertices. I would have the point 0, positive pi on 2, and 0, negative pi on 2 to complete my square. All right, are you happy with that question? All right, question 3. Find the equation of the tangent to y equals tan 2x at the point on the curve where x is equal to pi over 8. Okay, now I am going to have to find the y value that goes with that x coordinate. I might find that first this time. So let's sub in here the pi over 8. So it'll be tan of 2 pi over 8, which is pi over 4, but anyway. What does that equal? 1. Yay. Okay, so let's now find the gradient. Oh, stopping. So we need to differentiate y equals tan 2x. How did you? Yes, good. Tan differentiates to sec squared. So it'll be y dash equals 2 sec squared 2x. Okay? Then I need to find that gradient at the x equals pi over 8. So I'm going to sub that in. Now, I can't really put sec into the calculator, so I'm going to turn it into over cos squared, because sec is over cos, right? 1 over cos. So that will be over cos squared of 2 pi over 8. Now the squared part, when you're putting it in your calculator, you can't put the squared there. You have to put brackets around the whole thing and put the squared on the outside. So brackets around here and a squared out there, so type it in, because that's what that squared means. Yes? When you differentiate, you have to differentiate the function in here to the 2, because the other one didn't have a number in it, so that's why they have changed. Differentiate that comes out in front. Okay, just a sec. All right, did we get an answer? What did you get? No, we didn't get an answer. 4, yes, good. Okay, so I have got a gradient and a point. My gradient is 4, and my point is pi on 8, 1. So I can find the equation of my tangent. It will be y minus 1 equals 4 bracket x minus pi over 8. And expand it out and move the 1 to the right. So 4x, 4 times the pi over 8 would become pi over 2. Is everyone okay with that? The 4 cancelling with the 8. And then plus the 1 over. Okay, there's a part B and a part C and a part D. Let's keep going. Part B. Find the x-intercept and the y-intercept of the tangent. All right, how do you find an x-intercept? When y equals 0. How do you find a y-intercept? When x equals 0. All right, let's sub it in. When x equals 0 into my tangent that I just found, I would get y equals 4 times x. The 4 times 0, that does nothing. So I'm just going to get minus pi over 2 plus 1. If you want to, you could get a common denominator, which would be, oh, look at that. I even put the 2 first, so I didn't have minus pi first, but, put it all together as one fraction if you want to. Okay? Okay, then I'm going to sub in that y is equal to 0 into my tangent. Actually, I should have done that over here because I'd have more room. So that would give me 0 equals 4x minus pi over 2 plus 1. Okay, let's move everything away from the x. We would have 4x equals a positive pi over 2 minus 1. Then we're going to divide everything by 4. So that would be pi over 8 minus a quarter. And if we make the one fraction like I did last time, it would be all over 8. So this fraction is being times by 2. So that will be a 2 pi minus 2 all over 8. Okay, so we've got my y-intercept and my x-intercept. Next bit, sketch the situation. Sketch the situation. Okay, we are sketching colours. We're just doing pink today, so I don't think I can change colours. It's freezing. No, we're just doing pink, sorry. Pink for the rest of the day. Okay. We are drawing tan 2x. That was what this question was all about. What is the period of the tan 2x graph? What is the period of a normal tan graph? Pi is the normal period, and because we have the 2 in front of the 2x, you divide by that 2. So this graph is going to have a period of pi over 2. But the tan graph, that period is split over the origin. You have half of it to the left and half of it to the right. So we're going to have an asymptote, this is tan, at pi over 4 and negative pi over 4. Okay, so let's draw that. Pi over 4 and negative pi over 4. And the tan graph looks like that. That would just be one repetition. Obviously that pattern would continue if I wanted to keep drawing more of it down there. All right. We have found an equation of a tangent. The x value of my tangent was at pi over 8. So that's just halfway from the origin to that asymptote. Pi over 8, be right in the middle. So right here is where my tangent is, and it's going to come down like that. We want more colours, but we only have pink today. This is the point pi over 8, comma, what was my y value again? Was it 1? Look back, look back, look back. Where was it? Yeah, it was 1. Pi over 8, comma 1. Okay. Then I found, that was part A, where I found the equation of that tangent. Then in part B, I found the x and the y intercept. So my x, let's start with the x. My x-intercept was the pi minus 2 over 8. So that's going to be this one here. This is pi minus 2 all over 8 is that value. And then my y-intercept was this one, the 2 minus pi over 2. So that's going to be that value there. Hopefully you can see all the little bits and pieces happening. Okay, we still have a part D, which I'm going to read to you before I move the screen, because it says, find the area of the triangle formed by the tangent and the coordinate axes. The tangent and the axes, I want colours. Anyway, that little area in there. I want the triangle from my tangent to my axes. Okay, area of a triangle. It's a right angle triangle because it's going to the axes. So half base times height. The base, or whichever one will be first, the base would be the pi minus 2 over 8. And the height would be that one, but should be negative. That's a negative number. So we want a positive over that. We don't want a negative area. Okay? So let's put that in. Area equals half base times height. So half times, my base was the pi minus 2 all over 8. And then I want to times that by the height, which was the 2 minus pi over 2. But because I know that's negative, I'm going to put a minus sign in front of it so that that's actually a positive number, because we just want the length of it, not the direction of it. And that's what I want to find. That minus, if I want to get rid of it, you'd expand it into that bracket to become, the pi would be positive and the 2 would be negative all over 2. Expand it through the top. So versus the sign of those two things on the top. And then when you times it, you got a 1, and these two things are the same. So you have pi minus 2 in brackets all squared on the top, and then on the bottom you have 2 times 8 times 2, which is 32. So we have pi minus 2 all squared for the top and 32 on the bottom. And if it's an area, we will write units squared. What a great question. Number 4. Consider the curve y equals sine x plus cos x in the interval between 0 and 2 pi. Find the values of the function at the endpoints of the domain. The endpoint, this is my domain here. So the endpoints are these two extreme things here. So I want to sub those into my equation. So I'm going to sub in when x is equal to 0. That's my first one. Which would be y equals sine of 0 plus cos of 0. Sine of 0 is 0, but cos of 0 is 1. Okay, so that's just equal to 1. Then we sub in the other endpoint, which is 2 pi. And we have y equals sine of 2 pi plus cos of 2 pi. Again, sine of 2 pi is 0. It's the cos of 2 pi that has something, and it's 1 again. Because both of those curves start and end at the same point, basically, for the 0 to 2 pi domain. Part B. Find the x-intercepts of the graph. How do you find x-intercepts? You make y equals 0. Okay, so if y equals 0, I have 0 equals sine x plus cos x. Oh, we don't like having equations with sine x and cos x in them unless you're in extension 1 at the moment, because that's what we've been doing lots of. Okay, anyway, forget that. The rest of you don't care. All right, but we want to only make this in terms of one trig function. Can't have two in there. So, sine over cos equals tan. Let's move, which one do I move? Doesn't matter. Sine x equals minus cos x. I'm going to put one on each side of the equation. And then I'm going to divide the cos x across the other side. So sine x over cos x. I didn't divide the minus, so that would be equal to negative 1. So sine x over cos x is equal to tan x. I've been able to reduce my trig equation down to just one trig function, which should always be the goal. Okay? So then, solving tan x for negative 1. So in your calculators, maybe, you're going to inverse tan negative 1. But also remember, we are solving between 0 and 2 pi. I've got tan of something is negative, and tan is negative in 2 quadrants. Okay, so I really should be looking for a solution. Tan is negative here and here. So I've got to make sure I get 2 solutions. When you inverse tan negative 1, what do you get? Oh, you're in radians. Ah, okay. What was it? Sorry? Negative pi over 4. That's annoying. Okay. Negative pi over 4 means that it went backwards. So it went from here and it went backwards to that one there. Okay? So that does mean the pi over 4 part, pi over 4 is your reference angle. So pi over 4 in there. The alternative here is that you could do this in degrees if you're more comfortable doing it in degrees and then converting it into radians later. It's up to you. So if I want the 2 solutions from that little graph, this one, in radians, this is normally 180 minus that angle. We're in degrees. But if we're in radians, 180 is pi. I need to do pi minus pi over 4. What's pi minus pi over 4? 3 pi's over 4. Right? And then if I want this one, I would be doing 360 minus, but 360 degrees, that would be 2 pi in radians. So it's 2 pi minus the pi over 4, which is 7 pi over 4. So the other one is, and 7 pi over 4. Is that okay? I did it all in radians, which I know is not everyone's comfort zone. Okay, part C. Find any stationary points and determine their nature. Stationary points are when the derivative does what? Equals 0. I need a derivative. Y dash equals, my equation was sine x plus cos x. So what's the derivative of sine x? Cos x. And what's the derivative of cos x? Oh, you said that. Oh, thought I'd catch somebody, but no. You're very good. Good with your minus signs. Well done. Negative sine x. Okay, finding the stationary points are when y dash equals 0. So we're going to have cos x minus sine x equals 0. If I'm going to solve that, I've got to get those 2 trig functions into one again. So let's do the same trick. Let's put the sine x, because it's negative, let's move the sine x over to make it positive. Divide both sides by cos x. Cos divided by cos is 1. Sine divided by cos is tan. Is that okay that I did that straight away? Or do you want me to actually write the divide by cos? Is that all right? Okay, good. So then I want to solve that equation. This time tan is positive. It's a positive one. Tan is positive in here and in here. Okay, tan of, in degrees, it'd be 45. In radians, it would be pi over 4 again, but just in the other quadrants. Little pi's over 4 in there. So that means in the first quadrant, pi over 4 is my solution. To move it into the third quadrant, I need to do pi plus pi over 4, which is 5 pi over 4. Okay, that's it. That's good. I found the solutions that are in my domain. Okay. They are I haven't found the y value. Should I do that now or later? Now. Let's do it now. Because they're points. I can't have points that are just x values. I've got to find the y values that go with them. So I'm going to sub in, and please write small, we still have a fair bit to do here. I'm going to sub in that x is equal to pi over 4 into the original equation. And I'm going to have to do it for the 5 pi over 4 as well, so that I can find where these points are. So y would equal, the original equation was sine x plus cos x. In radians, you can just type that in. And I think you should get root 2. Did you guys get that? All right, so my first point is pi over 4 root 2. Do it again for when x is equal to 5 pi over 4. Y equals sine of 5 pi over 4. And it's not actually the same. What do you get this time? Negative root 2. Okay, so my second point is 5 pi over 4 negative root 2. I'm still not done. Because, let's go back to the question. Sorry, I can't quite squeeze the leg. I'll shrink it down. The question was, find the stationary points, done that, these are the stationary points, and determine their nature. So when to determine their nature, you can either do a big long table, or you can do it with the second derivative. Sorry, oh yeah. You can kind of tell, based on the y values, it kind of gives it away, but unfortunately, they expect you to show it. You can't just, yeah. Let's do it with the second derivative, because we like differentiating. Oh, we do. Yes, all right, second derivative. I prefer the second derivative. I find it fast. I think it's fun. I don't know. I think it's faster. All right, this is the first derivative. So cos x minus sine x. So when I differentiate the cos x, I'm going to get negative sine x. And when I differentiate the negative sine x, I'm going to get, it's still negative, negative cos x. So they're both negative now. Then I'm going to test each of them. So testing when x is equal to pi over 4. That was my first solution. In my second derivative, minus sine pi over 4 minus cos of pi over 4. When you type all that in, you get, do you want me to tell you? You get negative root 2. The number itself is not important. The minus sign is what gives it away. Because it's a negative, because that is less than 0, that means that that is a maximum at the pi over 4 comma root 2. Now I have to do that again for the other one. So when x equals 5 pi over 4, in my second derivative, I have negative sine 5 pi over 4 minus cos of 5 pi over 4. And this one makes the positive root 2. Okay, so because that is greater than 0 means that there is a minimum at 5 pi over 4 comma minus root 2, which is probably what you expected based on the y values that we found. Anyway, that was quite a bit to squish in there. I hope you fit that in. Okay, we have a part D. Find any points of inflection. Aren't you glad we found that second derivative? Yes. Because to find the point of inflection, what do we do? Yes. When the second derivative equals 0. So, my second derivative was minus sine x minus cos x equals 0. Again, don't like having sine and cos in there, so I'm going to have to turn it into tan yet again. So let's go sine x, move it across, make it positive, equals negative cos x. And then I divide both sides by cos. Sine divided by cos is tan, and minus cos divided by cos is negative 1. So that equation looks familiar. We kind of already know those solutions. They're the same ones as before. So the first one, but they're in the, this is exactly what we did here. We already did it. Tan x equals there, minus 1. So it's the exact same solution as that one. So it's going to be, I won't do it all over again, it's going to be 3 pi over 4 and or 7 pi over 4. If you're doing a point of inflection, oh, do I have room? You have to check the concavity changes. Do we have room? It's really naughty not to do it. We can squish it in. We can squish it in. Yes? Okay, I'm going to squish it over here. Okay, so we're going to have x values, second derivative, and we're checking that the concavity, can't spell concavity apparently. Concavity, squished in there. I want to see what happens. So, what have I got? I've got 3 pi over 4, and I've got 7 pi over 4. And I need to check what's happening around it. Oh, can I go to 0? Am I going to bump into another one? Probably better not go that far. So how about we just go over to pi over 2 here. 6 pi over 2, that'd be 3 pi over 2 would be in the middle. And 7 pi over 2, that would be 2 pi on the end. Just filling in the gaps. No, you don't have to. Okay, so when you sub in the 3 pi and 4 and the 7 pi and 4, they should be zeros. When you sub in pi over 2, I don't have the exact number written down, but it is going to be concave down there, which means that it is going to be, second derivative is going to concave down, which means the derivative was negative. So that was the point. 3 pi over 2 is concave up, so that one's a positive, and then the 2 pi is concave down again, so that's a negative. So what we're needing to see in the table, again, you can find the exact value if you want to sub that back into your thing, if you want the actual numbers. But you're after the positive and negatives, you're checking the concavity to make sure it's changing from concave down to concave up. So it is changing between each of them. So the points that I found are points of inflection. You have to check that, because usually if you don't, they will penalise you. All right, so last thing to do is to sketch our curve. Between 0 and 2 pi. So I'm going to go pi in the middle. Oh, that's not even, is it? About there, maybe. 2 pi. Now, I have got measurements that are going up by, like, all these over 4 business, right? So I need to go up in quarters of my pi here. So I'm going to have pi over 4. And then it's going to be 2 pi over 4, which is the pi over 2. And then 3 pi over 4. Keep counting up by pi's over 4. So then 1, 2, 3. So after 4 pi over 4 is the pi. So it'll be 5 pi over 4. The next one's 6 pi over 4, but that simplifies to 3 pi over 2. And then 7 pi over 4. Okay, so I've gone up by pi over 4 each time. My graph, if we think back through here, my graph starts and ends at 1. Okay, so we need that. We also have, we found that in part A. We also have the turning points, these turning points to put in there, stationary points, at root 2, so that's like 1.4, and minus root 2, minus 1.4. Okay, so I need some things on here. I'm going to need maybe go 1, 2, negative 1, negative 2. My graph starts at 1. I have a turning point. My first turning point that I found was pi. Oh, sorry, I should put the end. It also ends at 1. There you go. Starts and ends at 1. My first turning point was at pi over 4 root 2. Pi over 4 root 2 will be about there. Because if root 2 is in here, that's about 1.4 where I put that. And then my other turning point is at 5 pi over 4 minus root 2. So that's going to be about there. This is minus root 2. Okay, that's turning points. I also found x-intercepts were at 3 pi over 4, which is there, and 7 pi over 4, which is there. Well, this is filling in a lot of information for me, isn't it? Okay, and then I have a point of inflections at 3 pi over 4 and 7 pi over 4. They're already marked. So here comes my curve. Like that, like that, like that. Oh, bit wobbly. Like that. So these two here are points of inflection as well as intercepts. Okay, that's it. Okay, question 5 is our last one, but there's an A, B, C, D, E, F. Woohoo! Okay, question 5. Sketch the curve y equals x minus sine x after first carrying out the following steps. Step 1, write down the domain. Anyone? Good job, yes. Okay, sine x, right there's, it exists for all x. That's going to exist for all x. So they're both fine. We can just have all real x. All real x. So there's no asymptotes, no discontinuous points. This graph is going to be for all possible x values. Part B, test whether the function is odd or even. Best way to do that is to sub in f of minus x. Okay, so that would be minus x minus sine, of minus x. Now this is, that's not meant to have that big line there. This is going to test your brain. Sine of negative x. When I put a negative angle there, it means that I'm measuring it in my 4 quadrants. I'm going backwards into the 4th quadrant. Do you know what I'm saying there? So I'm going from my 4th quadrant, I'm measuring it a minus x, going backwards down there. Okay? So if I'm trying to do sine of something in the 4th quadrant, is it positive or negative? Negative. So I could say that sine of negative x is the same as negative sine of x. Because x is the reference angle, but it's negative because it's in the 4th quadrant. Okay, so it's negative and negative sine of x. The two minuses will make a plus. Okay. Now, if I can, it's obviously not even because that's not the same as what I started with. But if I can factorize a minus sign out of it, which I can, minus, and then I get x minus sine x. If I factorize the minus out, and that is the same as the original, which it is, it means it's odd. So you should write there that that's equal to minus f of x, and therefore odd. Okay, part C. Find any zeros of the function. Zeros are otherwise known as x-intercepts, which are when y equals 0. When y equals 0. So that means 0 equals x minus sine x, or x is equal to sine x. That's a bit nasty. When is x equal to sine x? Sorry, a lot of mumbling there. What was that? Very small angle is a good way of describing it. Let's have a think of the graph. The sine x graph does this that way, and it can do the same thing going that way. So that's what the sine x looks like. So y equals sine x is that one. And if I did y equals x, it would be a line with a gradient of 1 that goes through like that. Where are they equal? At 0. So my 0 is at x equals 0. You could also say, I don't know if I have room to say it though. Can I get rid of some of this? Or I could write it on the side. Is sine of x is going to be less than x anywhere where the x is greater than 0. And sine of x is greater than x anywhere where x is less than 0. We're finding out all sorts of information that's going to help us sketch this. Okay, so part D. Move, page, move. Record. Okay, part D. Examine the function's behavior as x approaches infinity and x approaches negative infinity. In other words, what am I hunting for? This is what we normally do for asymptotes, that's right. So we're finding out, but we know there aren't any, but we're seeing what happens as we go very, very big and very small. So as x is approaching infinity, my y would be approaching. Now my y equation was x minus sine x. So x is infinity minus sine of infinity. Oh dear. Sine of infinity. Okay, well, the biggest value that sine of infinity can ever get to, I'm going to call it alpha, that sine of infinity can ever get to is 1. Because the biggest the sine graph ever gets. So I have infinity minus 1, pretty sure that we can just call that infinity. Okay, so that means that that is basically approaching infinity. And as x is approaching negative infinity, we're going to have y approaching minus infinity minus sine of minus infinity. Again, sine of the biggest thing this could ever get to. Positive 1 doesn't really matter what you put in there. It keeps oscillating between plus 1 and minus 1. So this thing here can have a maximum value of 1 and a minimum value of minus 1, which means you're not adding or subtracting very much off here, but really just this thing here, the minus infinity. Okay, part E. Find any stationary points and determine their nature. All right, derivative time. What's wrong? No? My equation was y equals x plus, no, minus, x minus sine x. Yeah. You can't differentiate sec. Well, not without doing so. You can if you turned it into 1 over cos squared, which would be cos to the negative 2, and did a chain rule. But there's no formula for it, if that's what you're asking for. But anyway, we will leave that for now. Let's differentiate this one, which is not as difficult. Y dash equals, derivative of x is 1. Derivative of negative sine is negative cos. We're trying to find stationary points, so we're going to make our derivative equal to 0. So I'm going to move the cos x straight across. Cos x is equal to 1. This one, are we in degrees or radians? It doesn't say. Doesn't say. Let's do radians since we should. Okay. Cos of what equals 1? Think of your cos graph. You can't do it, well, you could do it by inverse cosing, but it'll only give you one of them. Cos of 1 starts at 0. Remember, when you cos of 0 is 1. And then when's it going to be 1 again? At 360, or in other words, 2 pi. And then it could keep going. It could be 4 pi. Or you could even go the other way, actually we should go the other way. Yeah. So let's put a few on the other side. Let's go minus 2 pi, 0, 2 pi, 4 pi. Just sneaking that minus 1 in. Because we're going to have to draw stuff on the negative side. We can have negative 4 pi there too. We do have to draw it. We do have to draw it. Okay. All right. Second derivative, because it says determine their nature. The second derivative, the 1 will disappear. What is the derivative of cos x? Negative cos x. Isn't it positive sine x? Oh, actually, wait, I won't differentiate it twice. Let's just do it from there. Let's do it from the other one. Okay, so y dash is always going to be greater than 0. I'm going to do it from here. So I want to see what is happening with the gradient here. Okay? Cos x, the biggest value it can ever get to is 1. Okay? So even at its biggest point here, I'm having 1 minus 1, so 0. 0 is the smallest my gradient is ever going to be. I mean, I could have a negative 1 in here, which means 1 minus minus 1 will be 2. But any way I look at it, my gradient is always going to be larger than 0, or it's going to be a positive gradient. Always. Always. Every value for x. So this whole curve is increasing the whole way. It's never going to turn back down. That's very important. Find any points of inflection. Okay, so now I do need my second derivative. So second derivative, when I'm differentiating negative cos, the 1 disappeared, remember? We do get back to a positive sine x. We make that equal to 0. So when does sine x equal 0? So sine x is 0 at 0. Then, this is the sine graph over here. It goes like this and keeps going. So 0, pi, 2 pi. But don't forget the negative ones. It could come this way, and I would have a negative pi and a negative 2 pi. So I could have, I'll just do negative pi, 0, pi, 2 pi. Any increment of pi, basically in the positive, negative direction. So if I want points of inflection, points. If you sub minus pi points into the original equation. The original equation was x minus sine x. So let's do this. What is pi minus sine pi? Or actually, we're doing minus pi. Let me write it down. So my equation was y equals x minus sine x. So I want to put in minus pi sine of minus pi. Just do it on your calculators. What does it equal? It's minus pi. So my first point is minus pi minus pi. Guess where the next one is? Put 0 in. It's 0, 0, yes. Where's the next one? Pi, pi. Where's the next one? 2 pi, 2 pi. Etc. This is the best graph you'll ever see. You ready? Let's draw it. Oh, I'm running out of room. Okay. 2 pi, 2 pi. So I'm going to go by pi's in every direction. Pi, 2 pi. I can even go to 3 pi. I'm going to go minus pi, minus 2 pi, minus 3 pi, pi, 2 pi, 3 pi. That's a great graph. You're going to love it. Sure, you're going to love it. And minus 3 pi. Okay, all those, all the stationary points back here. By the way, these ones do the same thing. I didn't write these as points. So this was minus 2 pi, and 0, 0. I forgot, sorry. 2 pi, and 4 pi. We can keep going. I didn't find the y values for those ones. Okay, so minus 2 pi, there is a a stationary point. And then I have another one at 0, 0. And I have another one at 2 pi, 2 pi. Now, in between, these ones are points of inflection. So minus pi and pi, minus pi, and pi. It looks like a straight line, but it's not. What is happening is that it's coming up, it's horizontally flat. They're actually horizontal points of inflection. They're not actually turning points, those stationary points. They're horizontal points of inflection. It comes up, it's stationary here, then it's going to inflect through that one, then come horizontal through there, inflect through that one, come horizontal through there, and it would keep doing that. It's like it's doing a little squiggle as it comes up. Did you like that graph? No, it's squiggling. Yeah, it probably should exaggerate it more. You see those points of inflection better. We made it. That was way longer than I